Lesson: Application of reinforcement learning in intrusion detection. Reinforcement learning has emerged as a potent methodology for addressing complex problems in various domains, including cybersecurity. Within this context, one of the most critical applications is in intrusion detection systems. An IDS is essential for monitoring and analyzing network traffic for suspicious activities and potential threats. The increasing sophistication of cyber attacks necessitates advanced and adaptive defense mechanisms, making RL an invaluable tool in enhancing the efficacy of IDS. Reinforcement learning, a subset of machine learning, operates on the principle of agents learning optimal behaviors through trial and error by interacting with their environment. Agents receive feedback in the form of rewards or penalties, which guide their learning process. This feedback loop enables the agent to develop strategies that maximize long-term rewards. The adaptability and learning capabilities of RL make it especially suitable for dynamic and complex environments like cybersecurity, where threats constantly evolve. One of the core advantages of applying RL to IDS is its ability to handle the voluminous and diverse nature of network traffic. Traditional IDS rely on predefined rules and signatures to detect intrusions, which often leads to high false positive rates and an inability to detect novel attacks. In contrast, RL-based IDS can learn from historical data and adapt to new threats without relying on static rules. For instance, an RL agent can be trained using a dataset of network traffic where benign and malicious activities are labeled. The agent learns to distinguish between normal and anomalous patterns, improving its detection capabilities over time. Moreover, RL-based IDS can be designed to operate in real time, providing timely responses to detected threats. This real-time capability is crucial in mitigating the impact of cyber attacks, as delays in detection and response can result in significant damage. For example, an RL agent can monitor network traffic continuously, adjusting its detection policies based on the latest observations. If a previously unseen attack pattern is detected, the agent can quickly adapt its strategy to recognize and mitigate similar threats in the future. In addition to real-time detection, RL can enhance the decision-making process in IDS by considering the cost of potential actions. In cybersecurity, actions such as blocking a suspicious IP address or isolating a compromised system can have significant operational implications. An RL-based IDS can be trained to balance the trade-off between security and operational continuity, selecting actions that minimize disruptions while effectively countering threats. This decision-making capability is exemplified in scenarios where the system must decide whether to raise an alert, block traffic, or take more drastic measures based on the confidence level of the detected threat. The use of RL in IDS also facilitates continuous learning and improvement. Cyber threats are constantly evolving, with attackers devising new techniques to bypass traditional security measures. RL agents can be updated with new data, allowing them to learn from recent attack patterns and stay ahead of emerging threats. This continuous learning process can be implemented through techniques such as online learning, where the agent updates its knowledge base incrementally as new data becomes available. This approach ensures that the IDS remains effective even as the threat landscape evolves. Implementing RL in IDS requires careful consideration of various factors, including the choice of reward functions, state representations, and learning algorithms. The reward function is critical, as it defines the feedback that guides the agent's learning process. In the context of IDS, rewards can be designed to reflect the accuracy of threat detection, the promptness of response, and the minimization of false positives. State representations, which capture the relevant features of network traffic, must be designed to provide sufficient information for the agent to make informed decisions. Common features include packet headers, flow statistics, and temporal patterns of network activity. The choice of learning algorithms, such as Q-learning or deep Q networks, depends on the complexity of the environment and the computational resources available. Despite the promising potential of RL-based IDS, there are challenges that need to be addressed to realize their full benefits. One of the primary challenges is the exploration-exploitation trade-off, where the agent must balance the need to explore new strategies with the need to exploit known successful strategies. In the context of IDS, excessive exploration can lead to high false positive rates, while insufficient exploration may result in undetected threats. Advanced RL techniques, such as epsilon greedy policies and upper confidence-bound algorithms, can help manage this trade-off by dynamically adjusting the exploration rate based on the agent's performance. Another challenge is the scalability of RL-based IDS, particularly in large and complex network environments. Training RL agents on high-dimensional data can be computationally intensive, requiring significant processing power and memory. Techniques such as parallel training, experience replay, and transfer learning can be employed to address scalability issues. Parallel training involves distributing the learning process across multiple agents or processors, while experience replay allows the agent to learn from past experiences by storing and reusing historical data. Transfer learning enables the agent to leverage knowledge gained from one task to improve performance on related tasks, reducing the amount of training data and time required. The integration of RL with other machine learning techniques can further enhance the performance of IDS. For instance, combining RL with supervised learning can improve the accuracy of threat detection by leveraging labeled data to train the initial detection models. Similarly, integrating RL with unsupervised learning can help identify novel attack patterns by clustering similar anomalies and learning their underlying characteristics. Hybrid approaches that combine multiple techniques can provide a more robust and comprehensive defense mechanism against a wide range of cyber threats. Real-world applications of RL-based IDS have demonstrated their effectiveness in various scenarios. For example, a study conducted by Mustafa et al. Implemented an RL-based IDS to protect critical infrastructure networks. The system achieved high detection rates and low false positive rates, outperforming traditional IDS. Another study by Nguyen et al. Applied RL to detect distributed denial of service attacks in cloud environments. The RL-based system was able to adapt to different attack patterns and maintain high accuracy in detecting malicious activities. In conclusion, the application of reinforcement learning in intrusion detection systems holds significant promise for enhancing cybersecurity. RL's adaptability, real-time detection capabilities, and decision-making prowess make it well-suited for the dynamic and complex nature of cyber threats. By continuously learning and improving, RL-based IDS can stay ahead of emerging threats and provide robust defense mechanisms. However, challenges such as the exploration-exploitation trade-off, scalability, and integration with other techniques must be addressed to fully harness the potential of RL in cybersecurity. As research and development in this field continue to advance, RL-based IDS are poised to become a cornerstone of modern cyber defense strategies.